welcome to the session. I am Dr. Sreekanth. Now, today we are going to discuss binomial and multinomial theorems. So, what is a binomial theorem? See, we know all are familiar with the binomial theorem. Just we are going to expand x plus y whole to the power of n as nc0 x to the power of just n y to the power of n minus 1 plus nc1 x to the power of n minus 1 y to the power of n minus 2. Like that, if we are going to proceed, so this is strictly speaking, just we are going to write it as nc0 x to the power of, if I am taking r is equals to 0, then I am going to take y to the power of n plus nc1 and x to the power of r is 1 and y to the power of n minus 1 plus nc1 x square y to the power of n minus 2 plus and so on plus ncn x to the power of n y to the power of n minus n. So this is the general expansion, binomial expansion of this, and we are going to write this as ncr x to the power of r y to the power of n minus r, and we have to consider the summation r is equals to 0 to n. That's we are mentioning here. So x plus y whole to the power of n, this is expanded as a summation of r is equals to 0 to n, ncr x to the power of n minus x power r y to the power of n minus r is a binomial theorem. So here we are going to change, we are going to write r is varying from 0 to n. Similarly, if you are going to expand, many variables, let us consider, I am just considering, let us, we have to consider the x plus y plus r, x1 plus x2 plus and so on, xn. So that we are going to write it as x1 plus x2 plus and so on plus xn whole to the power of n. So if you are going to expand this, then this is known as a multinomial theorem. So here in this multinomial theorem, a positive integer n will be there, and t is also any positive integer. Then the coefficient of x to the power of n1 into x to the power of x2 to the power of n2 and so on into xn to the power of n, if I am considering, then the coefficient of this, we are going to write it as, this is n factorial by n1 factorial and into n2 factorial into and so on, nt factorial, where n is any non-negative integer and ni is any non-negative integer which is less than n, Now, we are going to discuss this by using I'm going to prove this. So here, let us consider, I'm just taking, there are n among n objects. How many ways that we are going to select n1 is nothing but C of n1. So number of ways that we are going to select n1 items from Cn items. And this is the task one, first task. And the next another one is the remaining how many are there? n minus n1. So from this, if you are going to select n2, how many ways we are going to select? This is n2 ways. Then the remaining how many? N minus n1 minus n2. So we are going to get C of n minus n1 minus n2 and n3 we are going to select from this. So like this it is going to be continuing, like this it is going to be continuing, and we are going to consider the finally, let us we are taking n minus n1, n minus n2 and so on minus nt, and from this t minus 1, let us say I am going to select t. I am going to select t values. So this is the product rule. This is the first task and this is the second task. This is the third task and so on. This is a t minus 1 task. So here there is a product rule. By using the product rule, selection of first task, selection of second task, selection of third task and so on. So one after the other tasks that we are going to select, we are going to apply the product rule. Then this is nothing but since n1, that I am going to write it as n1 factorial, n factorial, and next by n minus n1 and into n1 factorial. So this is for this. And for this, once again, n minus n1 factorial, n minus n1 factorial, then by n minus and n minus n1 minus n2, and next into factorial. This is NCR. NCR is n factorial by n minus r factorial into r factorial. By using this, we are going to write this. So n minus r minus r factorial is nothing but n2 factorial. N2 factorial. Like this, we are going to get all the things, and finally we are going to get the simplification will be there. Say I am taking the next one, n minus n1 minus n2 factorial by and n minus n1 minus n2 minus n3 factorial into n3 factorial and so on. Then the last one also we are going to write. Then here n minus n1 factorial, n minus n1 factorial, and this will get cancelled, and this is also get cancelled finally with the next successive term. So finally we are going to get, what we are going to get is nothing but n factorial. This is the last term that we are going to get, n factorial by, this is n factorial by, all are going to be successively simplified. Then we are going to get nt factorial. Nt factorial we are going to obtain here at the end. And the next one is n minus n1 minus n2 minus and so on. nt minus 1 minus nt factorial. Nt factorial. So this is that we are going to get. So that means this is the coefficient of x1 plus x2 plus and so on plus xt whole to the power of n. If I am going to consider, this is the coefficient. This is the coefficient of x1 to the power of n1, x2 to the power of n2, and so on, xt to the power of nt. So for that, if you are going to expand this, then we are going to get this coefficient, and next we are going to get the remaining. See here, this is going to be simplified, the successive terms, and now we are going to get, this is also going to be simplified. Sorry, this is not correct. So here what I am going to get, n1 factorial will be there, and here I am going to get n2 factorial will be there, and so on. And the last one I am going to get n3 factorial, and so on. Last one is nt factorial. This I am going to get. It is not this. This is also successively simplified with the next term. And this one denominator also. So finally what we are going to get, only denominator n1 factorial, n2 factorial, n3 factorial and so on, nt factorial, that we are going to. And we are going to represent the same as like this, n and n1, n2 and so on, nt. So this also I am going to express this n factorial by n1 factorial into n2 factorial and so on. Nt factorial can also represent like this. represent like this. So this is the binomial and multinomial theorems. So here binomial, the coefficient is only NC0, NCR. So here x to the power of r and y to the power of n minus r. So here similarly, here it is a function of only two variables. It says two variables are there. So it is a binomial. We are taking x plus y. So more than two variables. So if you are going to apply the same principle, that is x1 plus x2 and so on plus xt whole to the power of n, if you are going to expand, then this is nothing but the coefficient of x to the power of n1 into x to the power of n2 into and so on x to the power of n xt to the power of n. Now let us consider there are some problems will be there. Then based on this multinomial theorems and the next binomial theorems, we are going to solve some of the problems. So first one is NC, this is NC0 plus NC1 plus NC2 and so on, which is equals to 2 to the power of n. It is mentioned as 2 to the power of n. We have to prove this. So the first one is, what is x plus y whole to the power of n? As we specified, this is nothing but NC0, NCR, x to the power of r, y to the power of n minus r. So r is equals to 0 to n. This we are specified by the last one. So here we mention this is by using this NCR, x to the power of r, y to the power of n minus r. So now I am just writing here. So just I am going to substitute, put x is equals to 1, y is equals to 1 in that expression. So 1 plus 1 whole to the power of n is equals to summation NCR 1 to the power of r, and next another one is 1 to the power of n minus r. So r is equals to 0 to n. Now this is only I am going to get NCR. So now r is varying from 0 to n. So now this is going to get NC0 whenever r equals to 0, then NC1 plus NC2 and so on, plus the last one is NCN. So NCN, this is nothing but 2 to the power of n. So this is the required result of this. Now in the second one, while considering the second one, let us call this as equation 1, and the second solution, if you are going to consider, in that I am just to substitute, put x is equals to minus 1, y is equals to 1. So if I substituted that, then minus 1 plus 1 whole to the power of n, and then summation NCR minus 1 to the power of r, 1 to the power of n minus r. Now this is summation NCR, and r is equals to 0 to n, and of course minus 1 to the power of r. So now this is, I am just taking r is equals to 0, NC0 minus 1 to the power of 0 is 1, and now n plus NC1 minus 1 to the power of 1 plus NC2 minus 1 to the power of 2, NC3 minus 1 to the power of 3 plus and so on, plus NCN minus 1 to the power of n. So now this I am going to NC0, it will be the same, minus NC1 and plus NC2 minus NC3 plus and so on. The nth term is minus 1 to the power of n, NCN. So this value will become 0. So minus 1 and plus 1 is, which is nothing but 0. So this is the final expression, final solution for the second one. So this is the identities, that what is the value of NC0, NC1 and so on, NCM, and what is the alternating series, NC0 minus NC1 and so on. What is the value of that? Now let us consider for solving some more problems which are related to the binomial or multinomial theorems. Now, find the coefficient of x to the power of 9 y cubed in the expansion of 2x minus 3y whole to the power of 12. So, if I am considering the first one, the solution is, so here, if I consider for this solution, for the first one, so we have to consider what is the x plus y whole to the power of n is equals to, so this is a summation NCR x to the power of r y to the power of n minus r. In the place of x, we have 2x. In the place of y, we have 3y. So I'm just substituting this. So what I'm going to get? 2x minus 3y whole to the power of n is equals to 12. So this is nothing but summation of 12CR, r is equals to 0 to 12. In the place of x, what we have? 2x to the power of r. In the place of y, minus 3y, n is 12 minus r. That we have to get. So here, this is nothing but summation of r is equals to 0 to 12 and 12CR 2 to the power of r, x to the power of r, minus 3 to the power of 12 minus r, y to the power of 12 minus r. Now let us concentrate on these two. So now we have to calculate, we have to find what is the coefficient of x power 9. So just I am going to substitute, put r is equals to 9. Whenever if I substituted r is equals to 9, then only it will become x power 9. And y is equals to, what about y, for what value of r if I substituted 9, then automatically y is 12 minus 1, minus 9. It will become y to the y cubed term. So just I am substitute, put r is equals to 9. So if r is equals to 9, if I am going to substitute, then this is 12C9, 2 to the power of 9 and minus 3 to the power of 12 minus 9 and x power 9, y power 12 minus 9. Subsequently, 12C9, 2 power 9 minus 3 whole to the power of 4 I am getting. 9, 10, 11, 12, 3. This is, I am going to get, see here it is 3. I am going to get it is 3. So then this is, so it is, this I have to take 3. Then, and x power 9 y cubed. So what about the coefficient of x power 9 y cubed is, this is the coefficient. So coefficient of x power 9 y cubed is 12C9, 2 to the power of 9 minus 3 to the power of 3. While we are going to simplify this, 12C9, 12 factorial, 12 minus 9 factorial into 9 factorial, and next I am just taking 2 to the power of 9 and of course minus, and 3 cubed will be there. So you are going to get whatever the value that we are going to get, that is the final answer for this. So here minus will be there. So whatever the coefficient, I am just taking minus. So this is the way that we are going to prove the first one. So next, suppose the second one is a multinomial. The second one is a multinomial. So while considering the second one, this one, say this is we have to consider. So for next, the second one, if I am going to consider, while considering the second problem, so here I am just taking, I am going to represent this is 12C, NC, R I am going to represent, or I can take it as NCR. In that form also I am going to represent. So because while we are going to consider the multinomial, so in that multinomial I am going to consider the coefficient of x1 to the power of t1, x1 to the power of n1, x2 to the power of n2 and so on. It will become n factorial by n1 factorial and n2 factorial into and so on, nt factorial, that we already discussed this. So based on that, we are going to solve the second one. So here, while I am going to consider the second one, x to the power of 11 and y to the power of c. What is the, see here the coefficient is n factorial by n1, n2 factorial and so on, nt factorial. This I am going to write in the place of like this, n factorial by n1 factorial, n2 factorial and so on, nt factorial. The alternate form of this is this. Now I am going to write, so here how many terms are there? Only 3 terms are there. So n is equals to 6 we have to consider. So this I am going to write 6 and n1. So what is the n1? We don't know. n1 and n2 also we don't know. And n3 also we don't know. 3 terms will be there. And related to that I am going to take. Then the expansion is, first one is 2x cubed whole to the power of n1 and minus 3xy square whole to the power of n2 and next z square whole to the power of n3 Just I am going to calculate x to the power of n1, x to the power of n2, x to the power of n3 coefficient. So this is just it is of the form x1 plus x2 plus x3 whole to the power of 6. So while considering this, we are going to consider the coefficient of x1 to the power of n1. I don't know what is n1. x2 to the power of n2, x3 to the power of n3. We have to find out. That n1, n2, of course, it is given as 11 and 4. That afterwards I am going to calculate, and n3 I am going to, but here n1 plus n2 plus n3 and so on. n1 plus n2 plus n3 will become n. And of course here n1 plus n2 plus and so on, nt will become n. In the generalized theorem. Now this I am going to write in the same way: 6 n1, n2, n3, then 2 to the power of n1 and x cubed to the power of n1. So it is nothing but x to the power of 3n1 minus 3 to the power of n2, x to the power of n2, y to the power of 2n2 and z to the power of 2n3. Now this I am going to write 6 n1, n2, n3. Then constant terms I am going to write first, and minus 3 to the power of n2. This is 1. This is another constant. Then x to the power of 3n1 plus en2. I'm just considering these two. And y to the power of 2n2, z to the power of 2n3. Now here I am just calculating what is the, find the term which contain x to the power of 11. X to the power of 11 and y to the power of 4. So here I am just taking 3n1 plus n2 will become 11. Because I need to find out the term x to the power of 11 coefficient and y to the power of 4 coefficient. And this is should become 11, and next 2n2 will become 4. So subsequently I am going to get n2 is equals to 2. While I am going to get n2 is equals to 2, 3n1 plus 2 is equals to 11. So 3n1 is equals to 9. Subsequently n1 is equals to 3. Whenever n1 and n2 are known, Then I am going to calculate what is the n3. So n1 is 3 and n2 is 2 plus n3 is equals to 6. So n3 I am going to get, so 6 minus 5, so I am going to get it is 1. So now I am going to substitute those three values. n1 is this, n2 is this, n3 is this. Now what about that coefficient will become, the coefficient will become 6, n1 is nothing but 3, n2 is nothing but 2, n3 is nothing but 1, and next 2 to the power of 3 minus 3 to the power of n2 is 2, and of course x to the power of, the sum should become 11, y to the power of, and then this will become 4, and z to the power of 2n3 is nothing but 2. So this is, then I am going to evaluate this. So this is nothing but 6 factorial by 3 factorial into 2 factorial into 1 factorial. So this is a 6 into 5 into 4 into 3 factorial by 3 factorial into 2 factorial. Subsequently these two get cancelled and then this is 2. So finally we are going to get 60. This is 60. This is 60. And into 2 cube. And of course 3 square. Of course 3 square and x power 11, y power 4 and z square. So the coefficient is just if you are going to simplify this. So 60 into, then this is, we are going to simplify that. Then whatever the value that we are going to get, there is a final coefficient, final answer for the coefficient of x to the power of 11, y to the power of 4, and of course z term is not given. So whenever x power 11 and y power x power 11 and y power 4, then z to the power of 2, the coefficient is this. The coefficient is this. So these are the some of the problems which are related to the binomial as well as multinomials. Binomial as well as multinomials. Now let us consider some more problems on multinomial, because the binomial is familiar. So now we are going to focus on multinomial related problems. Now I am going to consider, this is the first, to determine what is the coefficient of this one. X, y, z square. X, y, z square. What is the coefficient of this? And here, what is the, in this expansion, if you are going to expand, what is the coefficient of this? What is the coefficient of this? Now let us go for this. So here, what is the nth term? What is this? We don't know. n1, n2, n3, n1. There are 3 terms will be there. N is equals to 4 and n1 is we don't know. n2 also we don't know. n3 also we don't know. Then x to the power of, what is x2? X to the power of n1 and minus y to the power of en2 and minus z to the power of en3. Then we need to find out what is n1, n2, n3. See here what we have to compare, x to the power of 1, y to the power of n, z to the power of 2. So in that way, directly I am going to substitute n1 is equals to 1, n2 is equals to 1, n3 is equals to 2. Just this is the powers I am just concentrating on this, or else we can rewrite this into another form, n2, n3, n1, n2, n3, then 2 to the power of n1 minus 1 to the power of n2 and next minus 1 to the power of n3. Then let us focus on the variables, x to the power of n1, y to the power of n2, z to the power of n3. Now I am going to substitute n1 is equals to 1, n2 is equals to 1, n3 is equals to 2. So finally what we are going to get, 4, 1, 1, 2. Then this is 2 to the power of n1 is 1, minus 1 to the power of 1, minus 1 to the power of 2, x to the power of 1, y to the power of 1, z square. See the coefficient is, this is the coefficient. This is the coefficient. So now this I am going to write 4 factorial by 1 factorial into 1 factorial into 2 factorial. This I am going to write it as 2. This is a minus 1. This is a plus 1. X, y, z square. The coefficient of this is this. So 4 factorial is 4 into 3 into 2 factorial by 2 factorial. And of course minus will be there. Then it is a 2. So x, y, z square. Simply it is nothing but minus 1224. It is nothing but 4 factorial. So x, y, z square. So this is the final answer. So it is minus 24 is the quotient of x, y, z square. X, y, z square. So this is the way that we are going to solve the first one. And let us concentrate on the second one. Let us concentrate on the second problem. So here, how many variables are there? Here 1, 2, 3, 4, 5 constant also. If I am considering 5, then each variable that we have to consider the corresponding values as n1, n2, n3, n4, n5. So I am going to write this as 16. N is 16. Then we don't know n1, n2, n3, n4, n5. One is for A, one is for B, one is for C, one is for D, and another for constant term. Another one for constant term. So A to the power of n1. Next 2B to the power of n2. Next minus 3C to the power of n3. 2D to the power of n4. And 5 to the power of n5. 5 to the power of n5. Now we need to find out what are the values of n1, n2, n3, and of course n4, n5. So here it is already given. It is a square term. So a square term means just I am going to substitute n1 is equals to 2. Next b cube term is n2 is equal to 3. And c square term is n3 is equals to 2. And n4 is d is nothing but n4 is equals to 5. I am just taking n4 is 5. Then what about n5? n5 is nothing but n1 plus n2 plus n3 plus n4 plus n5, which is equals to n. So this is n1 is 2 plus 3 plus 2 plus 5 plus n5, which is equals to 16. So then I am going to 5 plus 5, 10, 12. So n5 is 16 minus 12, which is equals to 4. So it is 5, and the next one is n5 is that. Then I am going to substitute here. So it is 16, n1 is 2, n2 is 3, n3 is 2, n4 is 5, n5 is 4. And a to the power of n1 a square, and 2 to the power of n2. 2 to the power of n2 is 3, and of course b to the power of 3, and minus c in 3. n3 is equals to 2, and of course c square. 2 to the power of n4 is 5, and d power 5, and of course 5 to the power of 4. So now this is 16, 2, 3, 2, 5, 4. Then this is 2 cubed, minus 3 square means it is nothing but 3 square. Next 2 to the power of 5, then 2 to the power of 5, next 5 to the power of 4. Then the remaining is a square, b cubed, c square, d to the power of 5. So the quotient is this. So it is nothing but 16 factorial by 2 factorial into 3 factorial into 2 factorial into 5 factorial into 4 factorial and 2 cubed. 8, 9 into 2 to the power of 5. So this is the quotient of a square, b cubed, c square, d to the power of 5. So this is the quotient of this. So after simplifying this, so whatever the value that we are going to get, so that is the final answer of this. So this is the coefficient. This is the coefficient for a square, b cubed, c square, d to the power of 5. D to the power of 5. So these are the problems which are related to the binomial as well as multinomial theorems. So here, once again, we're just, what is a binomial theorem? So the binomial theorem is this. I'm going to consider this. X plus y whole to the power of n is NCR, x to the power of r, y to the power of n minus r. So this also I'm going to write it as summation of NCR, x to the power of r, y to the power of n minus r. And now I am taking more than two variables. This is t variables we are considering, and we are going to expand this t variables to the power of n. While we are going to expand this, the coefficient is x to the power of t1, x2 to the power of t2, and so on. X t to the power of nt, the coefficient is this. And this we are going to represent in this form. So these are the problems which are, this is the binomial and multinomial theorems. And now these are the binomial and multinomial theorems. And now if I am considering some of the problems, say the identities, if I am considering first one and the second one. So binomial theorem, just we are going to consider x plus y. Just by substitution, x equal to 1, y equal to 1, we are going to get the first one. X equals to minus 1, y equals to 1, we are going to get the second one. And similarly, we are considering what is the coefficient of x to the power of 9, y cubed. And of course, z to the power of something will be there. They are not given. They are not mentioned the full coefficient. So we have to consider the corresponding z power. And we have to expand this into the power of 12. And we are going to find what is the coefficient. And this is the multinomial. That means there are three variables will be there. X, y, z. And we are expanding the three variables about n times n is nothing but 6. Then what is the coefficient? And next, we have to consider some more problems on multinomial theorems. So, these are the things will be there under binomial as well as multinomial theorems. Now, let us consider the combinations with the repetitions. The next topic is combinations with repetitions. So, combinations with repetitions means while we are going to selecting the number of items, then that will be a repetition of the objects are possible. Suppose we wish to select with a repetition a combination of r objects. From n objects. We are going to select r objects. So, while I am going to select the r objects, once again I am going to keep the r objects into the n objects, and once again I am going to select the r objects. So that is why we are calling it as a combinations with repetitions. One time if I am going to select r objects, then finally I am going to get a number of what is the number of combinations that we are going to get, NCR combinations that we are going to get, and after that, once again, this is the distinct way that we are going to get. So here, the number of such selections, repetitions are going to be allowed. Then here, the number of ways that we are going to select is n plus r minus 1 CR. So repetitions are possible. Then it is nothing but repetitions are not possible in NCR ways. Then see here, n plus r minus 1 CR. Then while I am going to simplify this, so it is nothing but what is the coefficient is say this is earlier what we are going to take. NCR can be represented as like this. So NCR we are going to represent it as NCR. In that way, I'm going to write NCR. I'm just taking like this. And while we are going to simplify this, we are going to get this, and which is equal to this, equal to this. So I can write, they can take this, or else I can take this, which are both are equal. So which represents the number of combinations of n objects taken r at a time with repetitions allowed. Now, the following other two interpretations also of this number. One is n c of n plus r minus 1 r is equals to this. This is r plus n minus 1, and c n minus 1 represents the number of ways r identical objects. Another way I am saying, r identical objects can be distributed, or identical objects can be distributed among n distinct containers. There are n containers will be there. So in this container 1, container 2, container 3, and so on, there are n containers. So in this n container, r identical objects are going to be distributed. In how many ways that r objects are going to be distributed in n containers is nothing but in the same way. We can say that this is n plus r minus 1 cr. N plus r minus 1 cr ways that we are going to, the same question that we are going to. That means r n distinct containers, how many ways that r identical objects are going to be distributed in n different distinct or different containers, how many ways that we are going to distribute these many ways. And next, another way that we are going to say that the number of non-negative integer solutions, of the equation x1 plus x2 and so on plus xr is equals to r. So to solve, how many solutions of this equation is having non-negative solutions, non-negative integer solutions. That means greater than or non-negative integer solutions that we have to consider. So for that, how many non-negative integer solutions will be there? That is nothing but n plus r minus 1 cr. So in these two ways, either we can represent the same, either we can take this formula, either we can solve problems which are related to the first one or problems related to the second case. So in this way that we have to solve the problems based on the combinations with repetitions. So in the next class, we are going to discuss the problems which are related on combinations with repetitions. That we are going to discuss some of the problems. Now, so here the same thing, how many ways that we are going to represent the R objects. R objects are distributed, R objects are selected from n distinct objects. R objects are distributed to n distinct containers. N distinct containers are just to have to consider how many ways, how many solutions that we have to get. How many solutions that we have to get for the equation. So here this is n x1, x2 plus and so on, xn, x1 plus x2 plus and so on, xn. So is equals to r. So for this equation, how many solutions are possible? How many non-negative integer solutions are going to be possible? That also we can represent in that way. Okay. In the next session, we are going to discuss the problems related to this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.